Hello everyone, I am Abouzar Mirzaei-Paiaman. I am a postdoctoral researcher at Unicamp. The subject of this presentation is closed-loop field development, optimization of field development plan under uncertainty. My postdoctoral research is about evaluation of intelligent wells in model-based closed-loop reservoir management. In this research, I am following the 12-step methodology for closed-loop field development and management proposed by Professor Denis Schiozer. So far, I have had 3 contributions. The first one was a comprehensive literature review on closed-loop field development and management and was published in Journal of Petroleum Science and Engineering. The second contribution was an efficient multi-stage optimization procedure to find optimal quantity and location of wells. This one was also published in Journal of Petroleum Science and Engineering. The third contribution, which is ready to submit, is an iterative sequential optimization framework to find the optimal development strategy in large problems with complex parameterization. There are several motivations for this research. The first one is the diverse and high uncertainties at the initial development phase of Brazilian pre-salt reservoirs that demand robust development plans. The second motivation is broad decision variables related to wells and facilities that demand efficient optimization methodologies. And the third motivation is the high simulation runtimes associated with reservoir simulation due to the inherent heterogeneities and the physical phenomena related to WAG recovery in pre-salt reservoirs. The objective of presentation today is optimization of field development plan in cycle 1 of a closed-loop project. The size of the cycle depends on the quality of the models. In other words, a cycle ends when models are not valid anymore. For this life cycle optimizations, I have considered both design variables or G1 and control rules or G2. As design variables, I have studied quantity of wells, location of wells, platform fluid capacity, and ICV location. As control rules, I have studied WAG cycle duration, ICV setting, and production and injection rates. As a case study, I am working on Unicamp 2 benchmark case. Unicamp 2 benchmark resembles Brazilian pre-salt reservoirs. This benchmark has a high resolution reference model which represents a real field and is called Unicamp 2R. The benchmark also has a Unicamp 2D model, which is a case in the initial field development phase under uncertainties, and that has 1.5 years of production data for the wildcat well. Generally, information from 3 drilled wells has been used to build an ensemble of simulation models. Then this ensemble was data assimilated using production history of 1.5 years. Subsequently, operational uncertainties were included in the framework. After that, in order to reduce the time and cost of ensemble-based optimization, the whole ensemble was reduced to 9 representative models. At this research, we are working on these 9 representative models for a robust optimization of development strategy. We also include economic uncertainty into the analysis. Finally, we will implement the robust development strategy to the ensemble of models and to our reference model for risk analysis. Some general information about our research. We use iterative discrete Latin hypercube, or IDLC, as our optimization algorithm. This optimizer has two parameters. The first one is sample size, which we used 100 samples. The second parameter is a threshold cutoff, in which we used 0.2 as the value for this parameter. Our optimization is robust. It is performed on 9 representative models. The objective function is EMV, or expected monetary value. And CO2 water alternating gas, or wax CO2, is our recovery technique. And to reduce the cost of computations, we use a black oil fluid model in the simulations. This slide shows the optimization framework that we have developed. We have considered a wide range of decision variables. A sequential optimization framework was developed. The framework considers both design variables and control rules. However, the focus was optimization of design variables, as we are in the development phase of the field. Control rules of the wells that will be drilled first were optimized as well, and the optimization framework was practiced twice in 2 successive rounds. For parameterization of different variables, we have developed new methods. For parameterizing well quantity, in round 1, we distributed a large number of candidate wells over the reservoir. Each well was represented by a binary categorical value. 1 stands for drill and 0 means do not drill. In round 2, we fine-tuned number of wells by analyzing possible enhancement of the objective function through removal of a well or group of wells. As parameterization of well location, we developed a 2-stage optimization procedure. A region around each well was considered. Only a fraction of the grid blocks in each region was explored in the first stage of optimization. If necessary, then unexplored grid blocks were evaluated in a second stage. For parameterization of ICV location, we initially assumed that producers and injectors are equipped with 3 and 2 ICVs respectively. Each well was given a set of feasible ICV configurations, 10 for producers and 6 for injectors, and each configuration represented a predetermined ICV location arrangement. For parameterizing ICV setting, each ICV was defined by an individual control lump in our simulation. ICV setting can be controlled by assigning a flow restriction parameter ranging from 0 to 1 to the control lump. Each ICV in an injector was associated with 2 optimization attributes, and each ICV in producer was associated with 1 optimization attribute. Due to lack of time, I skip parameterization of other parameters. This slide shows the general progress and general evolution of the objective function in our optimization study. A large number of strategies had to be evaluated, about 7,900, and more than 71,000 simulation runs were performed to achieve the best development strategy. In this figure, each color shows optimization of an individual decision variable. Some characteristics of the best development strategy are presented in this slide. The best development strategy necessitated drilling 18 wells, in other words, 9 producers and 9 injectors. We observed that producers and injectors formed distinct groups. And also the field production was limited by the gas processing capacity. And also we found that during the water injection period, the ICVs tended to operate fully open. And also we noticed that the pattern of EMV evolution during optimization of wax cycle duration was different than other optimizations, and a clear convergence was not observed. This figure corresponds to this observation in which evolution of EMV in wax cycle duration optimization has been shown. After finding the best development strategy, the strategy was implemented to the Unicamp 2R, which is our reference model, and also the ensemble of compositional models for risk analysis and performance evaluation. In this figure, the vertical green line shows the response produced by the reference model, and the blue curve shows the response given by an ensemble of compositional models. Generally, the response of the reference model fell within the predictions made by compositional ensemble. Also, we found that representative models covered the entire range of NPV predictions by the ensemble. Representative models on this figure are shown by red points. And for other indicators, I mean cumulative oil production, cumulative water production, cumulative gas production, and cumulative water injection, in all cases, the response of the reference model always fell within the predictions made by the compositional ensemble. As conclusions and suggestions, the adapted framework for uncertainty quantification, data assimilation, selection of representative models, and optimization resulted in a reliable field development plan in cycle 1 of a general closed-loop field development project. Also, iterative sequential optimization made it possible to treat the very large search space and the complex parameterization requirements. And as a suggestion, due to the very high computational cost, use of assistive methods such as proxy and surrogate models in field development optimization is unavoidable. Thank you very much for your attention.